Hello viewers, so today's topic is differentiation, some important problems. Now in today's lecture we will solve some important problems uh, in which we find the derivative dy over dx. A function will be given to us and we are required to find the derivative dy by dx, or in some problems we have to find the second derivative, and in some more problems we will uh, find an expression which is a combination of these two along with the function y equal to fx. Clear? So let us start with some simple problems. So the first problem is, if sine inverse of root x plus 1 divided by square root of x minus 1 plus sec inverse of square root of x minus 1 divided by square root of x plus 1. We have to find the derivative y dy over dx. So viewers, here we have to closely examine this question. Clear? We have this expression and we have to find its derivative. Clear? Now here we are given y is equal to sine inverse this expression plus sec inverse of this expression. So after examining this question, let square root of x plus 1 divided by square root of x minus 1 is equal to, say, theta. So this implies that 1 over theta is equal to is square root of x minus 1 over square root of x plus 1. So we'll substitute these values here. So therefore y becomes your sine inverse of theta plus sec inverse of 1 over theta. Clear? So here we have assumed theta is equal to square root of x plus 1 over square root of x minus 1, and this implies 1 over theta is equal to square root of x minus 1 over square root of x plus 1. So we have y equal to sine inverse theta plus sec inverse 1 over theta. Clear? Now viewers, we know that sec inverse of, say, x is equal to cos inverse of 1 over x. Clear? This is by the properties of inverse trigonometric functions. So we'll apply this rule here. So y becomes sine inverse of theta plus, now this sec inverse is changed to cos inverse, and we have 1 over 1 by theta, which can be written as sine inverse of theta plus cos inverse of theta. So viewers, we know that from inverse trigonometric function, sine inverse theta plus cos inverse theta is equal to pi by 2. So therefore we have y is equal to pi by 2, which is a constant, and therefore dy over dx is equal to the derivative of pi by 2, which is a constant, so it is 0. So our answer is 0. Clear? Because the derivative of constant function is 0. So this is how we solve this problem. From the appearance of this question, it seems quite difficult, but if we closely examine this question, we see that this question can be reduced to this form, sine inverse theta plus cos inverse theta, and which is nothing but pi by 2, and then the derivative is 0. Clear? Okay. So viewers, let us solve this problem. Here we have y is equal to tan inverse of 1 minus x over 1 plus x minus tan inverse of x plus 2 over 1 minus 2x. Here we have to find the value of dy over dx. Viewers, again, as we have seen in our first example, we'll again closely examine this question, and we'll make use of the formula. Here I am telling you this formula: tan inverse of x plus tan inverse of y is given by tan inverse of x plus y over 1 minus xy. Similarly, we have tan inverse of x minus tan inverse of y is equal to tan inverse of x minus y over 1 plus xy. Clear? So viewers, sorry, this formula will be used in this expression, and this formula will be used here. Clear? Now see, this expression y can be written as tan inverse of 1 minus x 1 plus 1 times of x. X can be written as 1 times of x, and this is tan inverse x plus 2, and this can be written as 1 minus 2 times of x. So viewers, see, this expression becomes tan inverse of 1 minus x over 1 plus 1 multiplied x becomes tan inverse of 1 minus tan inverse of x. See, this reduces to this expression by using this formula. Similarly, here we have tan inverse of x plus tan inverse of 2. Clear? Because tan inverse x plus tan inverse y becomes tan inverse x plus 2 over 1 minus 2 times of x. So viewers, this becomes tan inverse of 1 minus tan inverse of x minus tan inverse of x, and here we have minus tan inverse of 2. So y equal to tan inverse of 1 minus 2 tan inverse x minus tan inverse of 2. Clear? Now sorry, now if we differentiate this function here, I am doing it here, so dy over dx is this is a constant, this is a constant, this is also a constant here, so we have the derivative 0 minus 2 times of derivative of tan inverse x is your 1 over 1 plus x square, and the derivative of this is 0, so in all we have minus 2 over 1 plus x square. So this is the required derivative of this expression. Clear? Now viewers, let us take this important problem. Here we have x is equal to square root of a raised to sin inverse t and y is equal to square root of a raised to cos inverse t. We have to find the derivative dy over dx, and here we see that this is an example from parametric differentiation. Clear? So let us do it. Here we will make use of this. Question can be solved by many methods, and what I am using here is we'll take the square of both sides here, or we can take the log of both sides. So we have log of x is half of log of a raised to sin inverse of t. Similarly, here we have log y is equal to half of log of a raised to cos inverse of t. Clear? Because we know that log of say a raised to square root of a is half of log of a. Clear? So here also the square root, in place of a square root we have half here. Similarly here we have half. Now again we'll use this property, log a raised to m is m log a. So we'll have log x equal to half of we'll have sine inverse of t multiplied log of a. Here we have log y, this is half, and we'll take here the term cos inverse of t, then we have log of a. Clear? Now log of x is equal to say k times sine inverse of t, and here also log of y is k times of cos inverse of t, where we have assumed that k is equal to half of log a. Clear? Half of log a, because this is a constant. Clear? Now we'll differentiate both sides. Here we'll differentiate both sides with respect to t. So we have 1 over x and dx over dt is equal to k multiplied 1 over square root of 1 minus t square, because the derivative of sine inverse x is 1 over square root of 1 minus x square. Similarly, here we have 1 over y and dy over dt is equal to k times, and here we have minus 1 divided by 1 minus t square. Clear? Now this expression can be written as dx over dt is equal to kx. This x is taken here, so we have kx over 1 minus t square, and here we have dy over dt, and we take this y to this to the numerator here, so it is minus ky 1 minus t square. So here we have 1. This is equation number 2. Now to find the derivative dy over dx, we have dy over dt divided by dx over dt. Clear? Because in parametric differentiation we find dy over dx equal to dy over dt over dx over dt. So dy by dt is minus ky over 1 minus t square, and here we have the sign of division, and here we have kx divided by 1 minus t square. Now we write it minus ky divided by 1 minus t square. This is multiply. We'll change this division sign into multiplication, and we'll take the reciprocal here, 1 minus t square over kx. So this term get cancelled, k and k get cancelled, and we are left with only minus y over x. Clear? So therefore dy over dx is equal to minus y over x, or we can rewrite this expression as x dy over dx plus y is equal to 0. Clear? So viewers, let us take one more example. So viewers, here we have the problem: if y is equal to a times e raised to 2x plus b e raised to minus x, and then we have to show that d2y over dx2 minus dy over dx minus 2y equal to 0. So what we will do here, we'll first find the first derivative. This is the first derivative. So we have a, the derivative of e raised to 2x is 2 e raised to 2x, plus b, here we have minus e raised to x. Clear? Because the derivative of e raised to minus x is minus e raised to minus x. So this is equation, say this is equation 1, this is equation 2. Now find the second derivative, that is d2y over dx2. So we have to differentiate equation 2. So here we have a, here we have 2. The derivative of this term is 2 e raised to 2x. Clear? And then we have minus b is here, minus b, and the derivative is minus e raised to x. So this expression is equal to 2 to the 4, 4a e raised to 2x, and minus minus plus, so we have b e raised to minus x. So this is equation number 3. Now we have to prove this expression. So we'll take the left hand side, and the left hand side is this side can also be written as y double prime minus y prime minus 2y. This can be written as y prime, this can be written as y double prime. Sometimes it is also written as y1. This is also written as y2. Clear? So y double prime is we have 4a e raised to 2x plus b e raised to minus x minus the value of y prime is 2a e raised to 2x minus b e raised to minus x. Then we have minus 2 here, and the value of y is a e raised to 2x plus b e raised to minus x. Clear? So viewers, we have 4a e raised to 2x b e raised to minus x minus 2a e raised to 2x plus b e raised to minus x. Then we have minus 2a e raised to 2x, and we have minus 2b e raised to minus x. So this is b e raised to minus x, b e raised to minus x. And here we have minus 2a e raised to 2ax minus 2a e raised to 2ax. So we have 4a e raised to 2ax plus this and this is added, 2b e raised to minus x minus 2a e raised to 2x, and this will be added here, and we have minus 2b e raised to minus x. So here we see that this and this get cancelled. Similarly, this and this get cancelled. We are left with 0, which is the value of RHS. And this is how we do this question. Clear? Viewers, let us take this problem. Here we have x equal to a cos theta and y is equal to b sin theta. We have to find d2y over dx2. Viewers, here I want to mention that I am taking a variety of questions, and you can practice more questions which are based on the questions which we are solving right now. So let us solve this problem. Here we have x equal to a cos theta. So first we will find the first derivative dx by d theta, that is minus of a sin theta, and dy over d theta is equal to b cos theta. Now again, this problem is from parametric differentiation, and dx by d theta is minus a sin theta. Similarly, dy by d theta is b cos theta. Now dy by dx can be given by dy by d theta over dx over d theta. Now dy by d theta is b cos theta over minus a sin theta. Okay, so this is minus b over a cos theta over sin theta is cot theta. So viewers, if we are asked to find only dy by dx, then this is the answer, or this is the solution. Suppose we want to find the value of dy by dx at theta is equal to pi by 4. So we'll straight away substitute the value of theta here. We have cot of pi by 4 here, and minus b by a multiplied 1, because cot pi by 4 is 1, so it is minus b by a. And similarly, for other values of theta, we can find the value of the first derivative. The first derivative denotes the slope of the tangent. Slope of the tangent. Clear? So here we have dy by dx equal to minus b by a cot theta. But viewers, here we have to find the second derivative. Clear? So the second derivative is d square y over dx square, and the second derivative is given by differentiating the first derivative. Clear? And the first derivative is dy over dx is minus b by a cot theta. Clear? So here we have minus b by a, so derivative of cot theta. Clear? Now viewers, here we can write minus b by a, since this is cot theta and this is x. So first we have to differentiate this cot theta with respect to theta. So we write it like this: cot theta. First we will differentiate with respect to theta, then we'll have d theta over dx. Clear? So let us write here. Okay, so we have the second derivative is minus b by a. The derivative of cot theta is minus of cosec square theta. Clear? And what is the value of d theta by dx? D theta by dx can be obtained from here. So we take the reciprocal here. So this is 1 over minus a sine theta. Clear? So viewers, we have y double prime is equal to, this is minus plus, and again we have minus, so we have here minus. So b over a square, b over a square, and 1 over sine theta again becomes cosec theta. So we have cosec of cube theta here. So this is the required value of second derivative. Clear? We can write this as minus b by a square equal to 1 over sine cube theta also. Clear? Suppose we have to find the value of that second derivative at theta is equal to, say, pi by 2. Then what will happen? We will have equal to minus b over a square multiplied 1 over sine of cube of pi by 2. Clear? So viewers, then we will have minus b over a square multiplied sine pi by 2 is 1, so it is 1 cube, so it is minus b over a square. This is just for extra information, because sometimes the question may be asked in this manner also. So we have y double prime at theta equal to pi by 2 as minus b over a square. Clear? Viewers, let us take this problem. Here we have y equal to log of x plus square root of x square plus 1, and we have to prove this expression equal to 0. So here we see that we have to find the first derivative as well as the second derivative here. Clear? So let us find the first derivative and second derivative, and then we will substitute the values in equation. We say this equation is 1. So the first is the first derivative here, dy over dx. So here we have this is say x. So we know that the derivative of log x is 1 over x. Clear? So we'll make use of this formula here. So we have 1 over x plus square root of x square plus 1, and then we will differentiate this function. Clear? We can write it like this: x plus square root of x square plus 1. Clear? So here we have used the chain rule. So first we have used the formula for the derivative of log x. The derivative of log x is 1 over x. Clear? Now we differentiate this one. So we have 1 over x plus square root of x square plus 1 multiplied. Here we have 1. The derivative of x is 1. The derivative of square root of any function is 1 over 2 times the square root of that function. And then the using chain rule, the derivative of x square plus 1, which is 2x, and the derivative of 1 is 0. So we have simply 2x. Clear? Now 2 and 2 get cancelled. So we have 1 over x plus square root of x square plus 1 multiplied. Here we have 1 plus x over square root of x square plus 1. Clear? So here we have 1 over x plus square root of x square plus 1 here, multiplied, we take the LCM, so we have x square plus 1 plus x divided by square root of x square plus 1. Clear? So here we see that this term and this term will get cancelled, so we are left with 1 over square root of x square plus 1. So dy over dx is equal to 1 over x square plus 1. So this is equation number 2. Clear? Now viewers, sorry, here we will take this, we can also differentiate both sides with respect to x, but here we'll take this square root of x square plus 1 to this side. So we write it like this, x square plus 1, and then we have dy over dx equal to 1. Clear? So this is an important step. This step is very important. So we can also differentiate both sides with respect to x in order to get the second derivative, but if we are multiplying this factor with dy over dx, then this will make our task easy. Clear? Now we differentiate both sides with respect to x. Clear? So now we will differentiate okay. So here's now we'll differentiate both sides with respect to x. So this is the product of two functions. This is f and this is g. So we'll use the product rule here. Okay? Clear? So square root of x square plus 1, first function, derivative of this function. So the derivative of this function is the second derivative. Clear? Plus second function and derivative of this function, and derivative of this function is 1 over 2 square root of x square plus 1 multiplied 2x plus 0, because the derivative of 1 is 0, so we have 2x, and equal to 0 because the derivative of this one is 0. So I think this step is clear to you. We have two functions here. We differentiate both sides with respect to x. The derivative of 1 is 0. So first function, derivative of this. So derivative of this is d by dx of dy over dx. So which can be written as d2y over dx2. And then second function, derivative of this function. So the derivative of square root function, always remember the derivative of square root function, say x is always 1 over 2 root of x. Clear? So here's so we have this step. Now we'll multiply this whole equation with this factor, x square, square root of x square plus 1. So this factor will become x square plus 1 only. This is d2y over dx2. Here when we multiply this by this factor, so this factor get cancelled, and we have half, this is plus, this is half, this is 0, this 2 and this 2 get cancelled. So when we multiply this by this, so this get cancelled and we are left with only x dy over dx equal to 0. So this is our required result. This is our required result. Clear? Okay. Now let us take another question. Viewers, let us take this important example. If tan inverse of x square plus y square is equal to a, we have to find dy over dx. So here also I would like to um, mention that whenever we do a problem, we first study the problem and we see the appearance of the problem, and we take a close look at the problem, how it can be simplified. Clear? So here also we see that if we take this tan inverse to this side, clear? So what we will have, we'll have x square plus y square is equal to tan a, and tan a is a constant, Now we have x square plus y square is equal to some constant, say c, where c is tan a. Now we differentiate both sides with respect to x. So what we get? We get here 2x. The derivative of y square is 2y dy over dx, and the constant, the derivative of this constant c is 0. Viewers, always remember, if we have a function y equal to fx, this x is called independent variable, and this is called dependent variable. So always remember, the derivative of x square is 2x, because x square is differentiated with respect to x, but the derivative of y square, because it has to be differentiated with respect to x, with respect to the independent variable, so this is always 2y times dy over dx by chain rule. So here we have written 2y dy over dx equal to 0. So dividing both sides by 2, we get x plus y dy over dx equal to 0. So y dy over dx is equal to minus x, and we can write dy over dx equal to minus x over y. So this is the required value of dy over dx. Clear? Viewers, let us take this problem. Here we have y equal to sine inverse x square, and we have to prove that 1 minus x square, the second derivative here, minus x dy over dx minus 2 equal to 0. Now this expression can also be written as 1 minus x square double prime, because the second derivative can be represented by y double prime, x y prime minus 2 is equal to 0. Clear? So let us do it, and here we have y equal to sine inverse x whole square. So dy over dx is, first we'll differentiate this one. We'll have 2 sine inverse of x, because we apply this formula here, d by dx of x square, which is 2x. Clear? So first we'll differentiate this function by using this formula. So this is 2 sine inverse x. Then we differentiate sine inverse x, and the derivative of sine inverse x is 1 minus x square. Clear? Viewers, the concept of chain rule is very important, and you see here whatever questions we are solving, we are dealing with chain rule. Clear? So this is sine inverse x whole square, so the derivative is 2 sine inverse x. Then we differentiate sine inverse x with respect to x. The derivative of sine inverse x is 1 over square root of 1 minus x square. Now see, this is equation number 1. So viewers, now what we will do, again as in the previous example, we saw that we multiplied, or we have transferred this term to this side. So we'll again do the same thing here. So we'll transfer it to this side. So we'll have 1 minus x square, then we have dy over dx. Here this is dy over dx. Clear? This is dy over dx, and equal to 2 sine inverse x. Clear? This is equation number 2. Now we differentiate both sides with respect to x. So what we will get here, again we will take this as first function, this as second function, as we have done in previous example. So this is 1 minus x square, derivative of dy by dx is this, plus dy over dx, second function, derivative of first function is 1 over square root of 1 minus x square, multiplied, sorry, here it is half. So we have here 2 times of minus 2x equal to the derivative of sine inverse x. So this is 1 over 1 minus x square. So always remember, the derivative of sine inverse x is 1 over square root of 1 minus x square. Okay. So I am explaining once again. We have y equal to sine inverse of x whole square. Then we differentiated it both sides. We get this equation. Then we take this term to this side, and we have the equation 2. Then we differentiated both sides. Here we have applied the product rule. First function derivative of second function plus second function derivative of first function. Okay, and here 2 is a constant, and the derivative of sine inverse x is 1 over square root of 1 minus x square. Now here this 2 and this 2 get cancelled, and we have 1 minus x square. The second derivative, I am writing this, I am writing y double prime for d2y over, sorry, this is dx2, and we have minus x over square root of 1 minus x square, and this is y prime is equal to 2 over square root of 1 minus x square. Clear? Now we multiply this whole equation by this term, square root of 1 minus x square. So here's what we will get. This term will become 1 minus x square. Clear? 1 minus x square double prime. Here it get cancelled, so we have x multiplied y prime, and here again this term will get cancelled, and we have 2. Now we take this 2 to this side, that is towards to left hand side. So we have 1 minus x square, y double prime minus x multiplied y prime minus 2 equal to 0. So this is the required result. Clear?